2.3 is on page 127, talks about functions. This is a brief introduction to functions. We're going to talk about a few things that we need for this course. Definition 1, let A and B be non-empty sets. A function f from A to B, we write it this way, is an assignment of exactly one element in B for each element in A. So for each element in B, it should map only to one element in A. It can't map to more than one. We write f of A equal B if B is unique element of B assigned by the function f to every element A in A. Basically, you cannot have the same input value or x value having two y values. That can never happen. That's really how you look at it. Remark, functions are sometimes called mapping or transformations. They call them different things as we move on. Another definition, a function is a function from A to B. We say that the domain of f and B is the codomain of f. If f of A equal B, we say B is the image and A is the pre-image. That's like domain and range. The range or image of f is the set of all images of A. Also, if f is a function from A to B, we say that f maps A to B. So let's see if we're dealing with a function here. Determine whether f is a function from z, remember those are natural numbers, to real numbers. Well, A, we have an issue. If you let n equal any number other than 0, of course, let's say 2, then you're saying f of 2 equal 2, and you're saying f of 2 equals negative 2. Well, that's an issue. You can't have one x mapping to two y's, so no. This is not a function. B, if you say f of n equal the square root of n squared plus 1, well, here the outcome is always positive. Keep in mind, if you let x equal 2, if you let x equal 2, then f of 2 will be the square root of 3. So there is only one outcome out of this. So yes, this is a function. And for the last one right there, if I let n equal 2 or negative 2, that will be 1 over 0, which is not defined. You can't divide by 0, so this is not a function. If it's undefined, you can't use it. And we define for every value in B, there's a pre-image in A. Now, I'm going to set those up because we might need them later on, but we're not going to use them in this section. Definition 3, that is, let f1 and f2 be functions from A to R. Then f plus 1 and f times 1, f times f1 times f2 is also a function from A to R, and they're defined as follows, just like the algebra of functions. 1 to 1 is a different story. A function f is said to be 1 to 1 or an injection if and only if, so it goes both ways. If f of A equal B, that implies that A equal B. For all A and B in the domain of f, a function is said to be injunction if it is 1 to 1. They have a remark of how to show this. If you want to show that it's 1 to 1, what you do, you assume f of A equal f of B, and you need to show that A equal B. And you could say if A doesn't equal B, then f of A doesn't equal f of B. That's how you prove it. One more definition that's extremely useful, something we're going to use, the floor function, floor or ceiling function. So this is and other books write it like this as well. This is the largest integer less than or equal. So if it's on the bottom, less than or equal to x. And this is the greatest integer that is, oh, I said them backwards, didn't I? This is the greatest integer that is less than or equal to x. And this is the smallest integer that is bigger than or equal to x. So this is smallest or least integer greater than or equal to x. This is the largest integer less than or equal to x. So this all could be solved with a number line with ease if I take part A. Now sometimes they write it this way too. I want, so this is 0, this is 1, this is 2, this is 3, this is -1, that's all I need. If I take 1.1, it's right there. Since I'm looking at the least, I'm looking for the floor, the largest integer less than or equal to 1.1. 1.1 is not an integer. The smallest number that's less than or equal to that is an integer, is 1. If I look at B, 1.1 still, but if I'm looking for the ceiling, that is the smallest integer greater than or equal, the closest integer is 2. If I look at -0.1, -0.1 is right there. It's a floor, so less than or equal, that's -1. Here, if I go for the ceiling, it's going to go up, that is 0. If I look for the ceiling at 2.99, what is the smallest integer greater than or equal to 2.99? Well, that's 3, of course. And here, if I have -2.99, oops, I want the greatest integer that is, the smallest integer that's greater than or equal, that's -2. This right here, if I want to work it out, that is 1/2 plus, this is the ceiling, a half is right there. A greater than or equal is a 1. This is 3/2. 3/2 is 1.5. The greatest, no, this is the least. I didn't write it right. Here we go. This is the floor. So the smallest integer less than or equal to 1.5 is a 1. So this is a 1. And how about this one? This at half, a half is right there. The greatest integer less than or equal, that's a 0. The greater than or equal, that's a 1. That's 3/2. 3/2 is right there. Since I'm looking for a ceiling greater than 3/2, that's definitely a 2. Determine whether each of those functions from a, b, c, d to itself is 1-to-1. Well, let's see. F of a maps to b. B maps to a, very good. That's a condition. That's 1-to-1. You go mapping from a to b and b to a. C maps to itself and d maps to itself. Yes, that is 1-to-1. A maps to b and b maps to b. This is not 1-to-1. Why is that? If it's 1-to-1, the mapping has to go forward and backward identically. And if I go to C, A maps to D, B maps to itself, C maps to itself, but then D maps to D. So D is being mapped forward correctly, but backwards, it's not 1-to-1. So the map should be forward and backwards 1-to-1. Determine whether each of the following from natural numbers to natural numbers is 1-to-1. So if I look at A, that is 1 to 1. That's linear. If I look at, if I choose n1 minus 1 to equal n2 minus 1, then I'll get n1 to equal n2, which is f of n1 equal to f of n2. That works. Yes. If I look at 2, that's definitely not 1 to 1. And why is that? Because the square f of 3 and f of negative 3 give you the same result. They're both 10. That's not allowed. Cubic is fine. This is 1 to 1, yes. Because for every one x there's one y, and for every one y there is one x. You could say set f of n1 equal f of n2. Well, that is n1 cubed equal n2 cubed, and here you could cube root both sides and get n1 equal n2, so that's 1 to 1. But if I was to do that on b, for example, if I was to say f of n1 equal f of n2, that's how you set it equal. Well, that's n1 squared plus 1 equal n2 squared plus 1. The 1's cancel out. That's n1 squared equal n2 squared. That's n1 equal plus or minus the square root of n2 squared, which is plus or minus n2. So here you don't have n1 equal n2. You have n1 equal plus or minus n2, which is a contradiction. That's why this is not. And this is linear d, so n over 2. I was going to say yes, but I noticed that's a ceiling. So if I say, what's f of 3? F of 3, that's 3 over 2. That's 1.5. It's a ceiling. It's going to go to 2. And if I say, what's f of 3.5? Well, 3.5 divided by 2, that's going to always go to 2. So that's an issue. That's not 1 to 1. I almost didn't pay attention. If it wasn't for the ceiling, that would have been 1 to 1. That wouldn't be an issue at all. And those last conditions, consider these functions from the set of students in a discrete math class. Oh, hey, that's like you guys. Under what conditions is the function 1 to 1? If it assigns to a student mobile phone number, that would be 1 to 1 with the assumption that the numbers are not repeating. If you have two numbers that are the same, then that wouldn't be 1 to 1, of course, but generally speaking, numbers do not repeat. Student ID, that's definitely 1 to 1. School make sure that student IDs don't overlap. Final grades in the class, that depends. Normally it's not 1 to 1 unless no two students got the same grade, then that's 1 to 1. Hometown, again, that depends. You could say it is 1 to 1, assuming no two students are from the same hometown. And if two students are from the same hometown, then that would not be 1 to 1. And that's all we need out of this section.